Good morning, my name is Jordi Bonada. I'm going to present the paper Analysis of Pallet Rack Beam Members through a nonlinear GBT formulation with sectional constraint. This work is done by the Department of Strength of Materials and Structural Engineering from la Universitat Politècnica de Catalunya. Here you can see the main objectives of this work. First of all is the introduction of weld spots into a GBT geometrically nonlinear analysis by adding sectional constraints equation. In fact, this is quite interesting because some European manufacturers use open sections as a beam member, and these open sections have weld spots along its length in order to reduce the distortional deformation of the beam. The second objective is the introduction of nonlinear pure model spring into the GBT model to be able to reproduce the beam-to-column connection characteristics. Then we want to validate the GBT results with a shell finite element analysis. Because in fact, our final objective in this research line is the possibility to analyze a whole pallet rack structure using generalized beam theory. So in order to reach this final objective, what we need to do is to solve the different particularities of pallet rack structures, like these ones of here. All GBT analyses are carried out in MATLAB software, and whereas the shell finite element analyses are done in ANSYS software. In this slide of here, you can see the two issues that we want to focus in this work. First of all, here you can see an example of a beam-to-column connection. This is the column of the pallet rack structure with its perforations along its length, which are connected to the beam member through closure buttons. This kind of connections usually exhibits a nonlinear relationship between the flexural moment and the rotation angle, so it needs to be taken into account into the structural analysis. On the other hand, as I have said before, some European manufacturers use open sections as beam members, and they have weld spots along its length to reduce, as I said, the distortional deformation of the beam under a flexural load. First of all, I'm going to make a very brief overview of GBT. GBT, or generalized beam theory, is a beam theory which is able to take into account several effects that classical beam models cannot handle, like sectional deformations. So it's a very interesting approach from a structural point of view. Two main steps are required to perform GBT analysis. The first one is the cross-section analysis, in which the deformation modes and the classical GBT tensor are formed. Here you can see an example of a thin wall member, and you will observe the local bases used for each sectional wall. Here you can see the displacement field equations according to these local bases for each sectional wall. And one of the characteristics or the particularities of GBT, as you can see in these equations of here, is that the displacement field is obtained as a combination of the different deformation modes involved in the analysis. In fact, the superscript k corresponds to each deformation mode. And we only use a specific set of deformation modes. What we want, we can use only the deformation modes what we are interested to include in our analysis. So it's very, very, very interesting. You can also observe that these displacement equations are obtained by combining two different kinds of equations. There are a cross-shaped sectional equation and also amplitude functions of here. So this is one of the trademarks, one of the characteristics of GBT. At the bottom of the slide, you will see the set of strains used to carry out the geometrically nonlinear analysis. The second step is the member analysis, in which a true node beam finite element is used to solve the member equilibrium equations. These beam elements uses the amplitude function for each deformation mode as a degree of freedom in our system. At the bottom of the slide, you can see the equations to calculate the elemental internal force, as well as the tangent stiffness matrices to carry out geometrically nonlinear analysis. These equations of here does not take into account any kind of initial geometrical imperfection into our model. So let's see how we have add or introduce the weld spot into our GBT model, what we have done is to add sectional constraints equations via Lagrange multiplier method to reproduce the characteristics of the weld spot. Here you can see the main dimensions of the beam member and also detail of the weld spot. So what we do is to introduce these constraints equations in the two sectional nodes where the weld spot is located. We introduce the same global displacement as well as the same implied rotation for the couple nodes. In this slide, we were going to talk about the main characteristics of our GBT analysis. The cross-section has been discretized using 18 sectional nodes, as you can see in this picture of here, and weld spot is located between or couple. The constraints equations are coupled these two sectional nodes of here, the sectional node 2 and 17, these ones inside the blue box. Only 10 deformation modes are involved in the geometrically nonlinear analysis. These 9 of here are conventional deformation modes, whereas the last deformation mode corresponds to a natural shear mode. 32 longitudinal beam elements are used for all load cases. So the second issue that we want to focus in this work is the beam-to-column connection, which is mainly exhibits a nonlinear relationship between the flexural moment versus the rotation angle. So in order to introduce this behavior into the GBT model, what we have done is to use a nonlinear pure model spring. So we have obtained this nonlinear relationship experimentally. As you can see here, this is a picture of our experimental test. And once we have obtained the experimental results, which is the blue line of here, what we have done is to adjust a cubic polynomial curve, as you can see here, to have a good agreement between the experimental values and numerical ones. So once this polynomial is adjusted and these coefficients are obtained, what we have to do is to calculate the elemental stiffness matrix, tangent stiffness matrix for this nonlinear pure model spring, and they can be easily introduced into our global system. Here you can observe some characteristics of the shell finite element model during ANSYS. We have used the shell 181 element. Fine mesh are used, as you can see here. The beam-to-column connection has been modeled by using a nonlinear spring. In this case is the element combin 39, and the weld spot is simulated by coupling all degrees of freedom of two nodes. At both ends of the beam member, rigid plates are introduced, this blue mesh of here, which restrains the sectional deformation and the warping displacement of the end sections. 4 different configurations has been analyzed in order to evaluate, to assess the influence of weld spots in our structural response. The load cases and the boundary conditions are the same. The only difference between each 4 cases is the number of weld spots. And it is one simulation without weld spots, with 1 weld spots, 2 weld spots, and 3 weld spots located inside the red circle of here. Here you can see the main results we have obtained. First of all, I'm going to focus on the horizontal displacement of the beam member. This is the values obtained with shell finite element analysis, and these ones of here is with the GBT values. This is the case with the load for 2 weld spots, and we observe that there is a very good agreement between the displacement field obtained with shell finite element model and GBT values. On the other hand, in this figure of here, what we observe is this horizontal displacement along the longitudinal beam coordinate for the sectional node 4, this one of here, and we observe that the highest horizontal displacement is obtained for the case without any weld spots. If we include 1 weld spot, there is a clear reduction of this horizontal displacement, which is obviously related to the distortional deformation of the beam member. The same displacement is practically obtained for the vertical deflection in each case. After that, what we want to do is to analyze the influence of the beam-to-column connection in this horizontal displacement. So we have tested 3 different cases for the load case with 2 weld spots. The first one is assuming a perfectly rigid connection between the column and the beam, and then 2 different kind of connections, 2 different kind of semi-rigid connection, the connection S1 and S2, in which the S1 is stiffer than the S2 as you can see here in this figure of here. At the right part of the slide, you will observe this horizontal displacement versus the external force applied. This is the maximum horizontal displacement, which is obtained in the middle of the beam member. And you will observe, as first of all, the very good agreement between shell and GBT values, and also that the maximum horizontal displacement is obtained for the load case or for the connection for the most rigid or more stiffer connection. The perfectly rigid connection have a higher horizontal displacement than the other cases. Obviously, the vertical deflection behavior is totally different in each case. So, to sum up, here you can see the main conclusions of this work. First of all, we have seen that it is completely necessary to introduce the effects of weld spots and the beam-to-column connection behavior to properly reproduce the structural behavior of our beam member. We also have seen that the weld spots can be introduced into GBT geometrically nonlinear analysis by adding sectional constraints equations. On the other hand, the beam-to-column connection behavior can be reproduced as a first approach by introducing a nonlinear GBT pure model spring. We also observe that it's clearly recommended the use of weld spots if an open cross-section are used as a beam member in order to reduce this distortional deformation of the beam. And GBT can be a very useful analytical tool in order to analyze the best position or the number of weld spots that must be used. And finally, we observe that the beam-to-column connection behavior has a relevant influence on the distortional deformation of the beam. In fact, the higher horizontal displacement are found for stiffer connections. Thank you for your attention. Bye.